Hello, Wayland Middle School's Mr. Farley here, and I'm just going to run through a couple basic ideas around functions and not a function. I know you had a chance to go over this at one point last week, but I just want to kind of fill in a few gaps. Hopefully, everything will make some sense, and then you can do some practice on your own while I'm out. So I'm just kind of looking at the slides here, and the question's asking us which ones are functions. In this case, there were three of them. They are highlighted in red there already. But just the one thing to really pay attention to when given a table or a chart, please make sure you look at the input values. And if the inputs are not repeating, okay, then most likely we're going to have a function. So if we see here inputs here 0, 1, 2, 3, 4, nothing repeats here in the input, that's going to be a function. Second one, 2, 4, 6, 8, 10, nothing repeats. Here is the input. That would make it a function. Similarly, D is the same thing, nothing repeats, so that would be a function. And letter C here in the middle, I think you could see what's going on here. Oh no, 6's repeat and 7's repeat. Therefore, this is not a function. This would just be a relation. You heard Mr. Robinette talk about that at a previous video. But this here, it would just be, this would be considered a relation, not a function. Okay, so that was one thing I wanted to show you. Second thing here, when given ordered pairs, can we determine whether or not something is a function? Let's just look at it quickly. I see an input of 2, 4, 3, 6, and 2. Oh no, I see the 2's repeat here. Therefore, this would not be a function. However, I'm asking you to state what the domain of this relation is, and then the domain would just be what the inputs are. So I have an input of 2, 4, 3, 6, and 2. That's the domain. There's no need to repeat the 2 twice. Just have it listed one time. You put it in that set notation here with the brackets on either side. The range is the output. That would be the y values in the cases here. -3, 6, -1, 6, and 3. Oh no, I think you heard me say 6 twice. Don't repeat it. Just write it one time. That's all you need to do. So again, this is not a function, but we can also state the domain and the range. The domain is the input values. The range would be the output values. All right. That's one we're going to skip. But here, let's given a graph. If I asked you determine whether or not this is a function, these are the easiest ones to do because you just kind of take a look and see if the vertical line test works. Vertical line test is when you can place a vertical line anywhere on the graph. If it intersects a graph at more than one point, which it does in this particular case right here, that's a clear indication that this will not be a function. If you had a different graph where the vertical line would only intersect at one point only, then that would be a function. So vertical line test, super fast way to determine whether or not a graph is a function. Great way to do it. Another thing, mappings, a very easy way to determine whether or not a relation is a function. And you can do that by looking at the left oval would be the input, the right oval is the output. And if you notice, each input has only one output. Okay, that would make it a function. Uh, the looking the other way at like B, the input of A maps to two different outputs. It has multiple outputs. This would mean this is not a function. D is the same thing. A goes to multiple outputs, B goes to multiple outputs. Therefore, D is not a function. But if you look closely at C, you'll notice that A only has one output, C only has one output, and so does D. That would make it a function. So that's a way you could look at it with mapping as well. When we're talking about finding the domain from a map, all you need to do Really easy. This one is specifically asking us to find mapping for C. It's just the input, so it'd be the left oval that we're looking for. A, B, C, D are the uh, are the values in this oval. I think everyone notices A maps to a particular output, C maps to an output, and so does D. A, C, and D would be the domain. B is not even being used. It's not mapping anywhere, so we can basically ignore that. So the domain for C would be A, C, and D. A couple more things I wanted to show you, and this is a different question. This one's asking whether or not something is linear or not. So this is different. Before we were asking, is it a function or not? Now we're asking, is it linear? And it's really easy to determine whether or not something is linear, especially from a graph. So let's take a look at 3 different examples. I am positive everyone looking at this one here on the left, this is 100% linear because it is a graph of a line. All right, that is linear. If I asked you the question, is this line here a function? I hope everyone's thinking, well, I think it is because it passes the vertical line test. Wherever you put a vertical line, it will only intersect at one point. Therefore, this is a function. This middle one, is it linear? Well, I hope we're saying no because it curves. All right. It curves, any curve automatically not linear. Now let's change the question. Is this middle graph here a function? Well, if you take a look at it and you do a vertical line test, it will only intersect the graph at one point. Therefore, this would be a function. The last one here on the right is a little bit of a trick. This is not linear. It is not linear because if it's linear, it's only a straight line. That's all it is. Even though this one zigs and zags, this is actually a graph of an absolute value equation. This is not linear. But then if I change the question, is it a function? Ask yourself, does it pass the vertical line test? And the answer for this one is yes. So be very careful with the question that's being asked. All 3 of these are functions, okay, because they pass the vertical line test, but not all of those are linear. The only one that's linear is the first one on the left. Let's try a couple other things. Frequently, you are going to be deciding if something is linear or not by looking at an equation. And the best way that Mr. Robinette and I like to think about this is we say, nothing fancy is happening to the input variable x. And what's fancy operations? Well, those could be being raised to a power, a square root, absolute value, or x in the denominator. So when you look at these 5 examples, this is fancy notation. F of x is just fancy notation. It could be replaced with a y. Everyone would feel better if this said y equals 3x plus 7. But you're pretty sophisticated, so we will say f of x equals 3x plus 7. This is linear because nothing fancy is happening to the x. This here is an equation of a line. It's in the form y equals mx plus b. Number 2 is not linear because the x is in the denominator. That's something fancy going on there. That is a problem. This would not be a line. Number 3, I'm trying to trick you. The exponent of 2 is with this constant right here. I think everyone knows 7 squared is 49. So this could be y equals 3x plus 49. Everyone knows that slope-intercept form. Therefore, it must be a line. So this one, number 3, is linear. Number 4. Number 4 is nonlinear. The reason it's nonlinear is because there's a fancy power of 2 attached to the variable x. This is a square. This would result in a quadratic. All right, that would be a U-shaped graph. So this is not linear. And last but not least, number 5. Number 5 is, again, slope-intercept form. Y equals 1/3 x plus 7. Nothing fancy going on there with that x. This must be linear. Okay? So again, linear or not, please be careful. If it's being raised to a power, it will not be linear. All right. Well, power other than one. Okay. Square roots cause problems. Absolute values cause problems. And x in the denominators also cause a problem. Two more things on a table here to determine whether or not it's linear. Test the slope. If it's a constant rate of change throughout, then yes, this would be linear. Okay, so keep that in mind when testing, and I'll leave that up to you to determine whether or not this is linear. You can test it by checking the slope. Is it the same throughout from point to point? This is another example. Same idea. Test the slopes to see if there's a constant rate of change. If there is a constant rate of change, meaning the slope is the same between these points, then it will be linear. If not, then it's not linear. Okay. So that's the summary there for you. So hopefully we had a little refresher and a little review of that. You are definitely ready to take off with the unbelievable handout that we have for you today. It's called Fun with Functions. You honestly, if you take a look at Domingo, you can't spell functions without the word fun. All right. This is going to be great. Have a blast. You're going to try to get through a lot of these problems here today. Everything will be posted for you in Google Classroom as to which pages you should focus on for today's lesson. Hope you enjoyed the video. Take care.